Hey everyone, my name's Andy Wright. I am a research assistant or a grad student at CSAIL at MIT. I'm in Professor Arvin's lab, and we have recently started what we're calling our Riscy expedition. So the past semester, we made a 64-bit RISC-V processor with the IMAFD extensions. It supports machine, supervisor, and user modes. It boots RISC-V Linux with SV39 page virtual memory. We have tandemly verified it with the Spike ISA simulator. And it's all been written in BlueSpec System Verilog. In the same semester, it's been integrated into Arvin's computer architecture course, 6175. And it's going to be used even more in future iterations of that course. So this was a big task in its own, but it's just the starting point for us. So we're using this as the base for our Riscy expedition. So this expedition is 6 different aspects combined together. We're going to try to form a formal specification of the ISA or a subset of the ISA. We want to do such with an operational model. We want to construct formally verified processors or formally verified optimizations to processors. We're going to explore memory consistency models for RISC-V, including if RISC-V should have a weak memory model, and if so, which memory model. There's some desire to explore accelerators for the architecture. We're going to do some microarchitectural exploration to improve performance. And at the end of the day, we're going to be targeting ASIC. So we're going to be tuning microarchitectures to performance, power, and area numbers in ASIC. There's no concrete plans for a tape out yet, though. So throughout this initial design, we've been focusing on what we're calling verified design. So our plan is to get a working processor first, figure out why it's slow, and then make it faster without breaking it. So we're leveraging BlueSpec System Verilog, which gives us a very modular way of describing our processor. And it also gives us a great platform to add on to and make changes to. So simple changes in our processor may not break the whole thing, where a simple change in Verilog may break everything. So in our group, there's no separation of design and verification. All the design that is going on should be verified to be correct. So currently, we're using tandem verification, using some technology developed by BlueSpec Incorporated. But in the future, we're going to be moving to formal verification. So to give you some background information, so this is how we built this processor. This is how we got Linux booting. This is tandem verification. So we run our design, either a simulated version of it in Verilator or the design running on an FPGA, in tandem with the Spike ISA simulation. They have synchronized HTIF interfaces, so they see the same input and output at all times. Spike has been slightly modified so that its timer interrupts matches ours, and certain other behaviors that we have adopted, we have merged into Spike. So both Spike and our processor have been configured to output the program counter, instructions executed, what the data was, packets exchanged with HTIF, and the memory operations being performed, if any. So this has helped us find many bugs, including some bugs in booting Linux in our virtual memory system, that maybe a load at some instruction saw the wrong data because it was reading a page table entry that wasn't updated dirty correctly or something like that. And then thousands of cycles later, or millions of cycles later, the two programs diverge. So instead of catching the error a million cycles in the future, we catch it as it happens. So this is extremely useful to get Linux booting, but it's lacking in terms of complete verification. So if you have a highly parameterized design, what this is telling you is that your specific instance of your design that you tested works with the program that you're running on it the one time you ran it. And that's lacking for us. So we're moving to formal verification. So when we say formal verification, we're saying we are going to be constructing a proof that our processor matches a formal specification, or a proof that an architectural optimization that we have applied to our processor does not change the correctness of our processor. But this requires a formal specification for RISC-V. And this is not an easy task because there are a lot of odd cases that really need to be concretely decided before we can construct the formal specification. So throwing out some concrete examples. Our reference bits in page tables allowed to be speculatively updated or updated for speculatively accessed pages. So if your branch predictor says you're going to be running an instruction from a page that hasn't been accessed yet, are you allowed to set that bit even if that instruction isn't committed? That would completely change the formal specification because that would introduce this idea where you can have some speculative instructions that are changing the state in your processor that don't correspond to committed instructions. Additionally, a single instruction can result into 13 effective memory accesses at the top end. And this may even increase with a hypervisor depending on the implementation of the hypervisor. So how do these 13 memory accesses interact with each other? And how do they influence the memory model? So from here on, we're going to talk about some of these details we're looking at, and we're going to start with just memory models in general. So just a short overview, there's many different types of memory models that describe how multiple threads in a system see memory updates. There's strong models that are easy to understand, such as sequential consistency and total store order, but they restrict optimizations. There's weaker consistency models that permit hardware optimizations, but they're very difficult to understand in their descriptions. So like release consistency is described in terms of operations performed with respect to certain processors. And in Power and ARM, they have a very unclear memory model specification in their ISA. And it's sort of left to, you can't really assume much except for special cases. So for a formal specification, we really want simple operational definitions. That doesn't imply a simple memory model. It just implies that you have a memory model you can describe in simple terms. And we want them to be an operational definition such that legal behaviors must be observable in some abstract machine, and that the cores are performing one instruction at a time, atomically, and they perform them in program order. You may have local structures that brings out the reordering in your memory model, such as TSO. TSO would be the application of these cores and a store buffer that the cores can read from their own store buffer, but not their neighbor's store buffers. And fences in this model are reflected in flushing local buffers. So we're going to propose a new weak consistency model that we're calling WMM that will have, or that has a simple operational semantics that still allow load store reordering and almost all microarchitectural optimizations. So it's described with a store buffer and an invalidation buffer per core, and the loads and stores describe actions on these buffers, and fences describe how these buffers are flushed. This provides an easy-to-understand operational model between cores, but it misses those 13 loads and stores that each core can do and the interaction between those 13. So let's talk about those for a bit. So we're going to call those flavored memory accesses. So here's a subset of a simple processor pipeline. You have instruction fetch. It's going to read instructions to execute. You've got memory accesses. It's going to load and store data from your data memory. The RISC-V ISA specifies a fence instruction between data accesses and input-output accesses. So that implies there's a separate flavor of memory accesses for inputs and outputs. So so what we get from this is sort of uncached accesses, and the fences describes ordering between those operations. But at the same time, you have virtual address translation loads and stores. This looks a lot like 4 separate cores accessing the same memory. So it looks like this may also have a memory model, and we're hoping that it gets integrated with the same memory model. So diving a bit into some details with synchronization between these effective cores or flavored memory accesses, we see one example from the ISA for synchronization is sFINS-VM. So tandem verification helped us in many places. The biggest place it helped us was recognizing that there was a few sFINS-VMs missing from the Linux kernel. So with the specification of sFINS-VM, it's described from a programmer's point of view instead of hardware point of view. It's not a TLB flush. It's a synchronization between stores to the data and virtual address translation loads. So data stores coming before an sFINS-VM have to appear to the virtual address translation loads after the sFINS-VM. With those semantics, every time there's a write to a page table, you need an sFINS-VM before that translation can be used. But there's no instruction for the other direction yet. So a virtual address store, which comes from updating a page table entry as referenced or dirty, there's no synchronization between that store and a load from the kernel to see whether to see the new state of the page table entries. So we're proposing that there should be another flavor of sFINS-VM that works this opposite direction so the TLBs can cache data or dirty and reference bits. So we're looking really closely at these flavored accesses, and we're combining them into our memory model as a first step for a formal specification for the ISA. So there's other directions to this that are even further in the future. We have a team member that's looking into accelerators. He has been working on our BlueDBM machine recently in Arvin's group. That is a 20 FPGA machine with flash memory attached to each FPGA. He was looking into neural network acceleration, and he has decided that he wants to use a RISC-V core with a convolutional neural network accelerator or ISA extension for those applications. We have a big desire to do some microarchitectural research, and we're also, at the same time, we want to focus on ASIC implementations so that we're not leaving performance on the table in our designs. And one other aspect of this is education, actually. Arvin's got a great computer architecture course that's using RISC-V right now, and we want improvements that this expedition finds to find its way into that course as well. Any questions?
Questions for Andy?
Is this open source?
So it's not open source at the moment. It's definitely something we want to tackle, but we have to solve a problem first. And the problem is with education. So the 6175 course, the final project for the past few years, has been pretty advanced to the point where, just to throw out some concrete examples, one of the years I TA'd it, they were given an in-order processor. They had to make it into an out-of-order, they had to make it into a multi-core processor with non-blocking caches. We have those non-blocking caches in this processor, and we don't want to, at the moment, we want to figure out how we can keep those final projects interesting without, and still have this processor out in the open. So we're trying to figure out how that's going to work.
Tommy Thorne, unaffiliated. The weak memory model that you propose, is that more constraining than any existing implementation, or is that sort of the weakest practical model that you can imagine?
So it's a little bit more constraining. I don't have the details with me at the moment. I'm not the lead for that portion of it, but I can definitely get you in contact to get down to some of the details of it. There's still some open-ended portions of the memory model that we're trying to figure out before we make it public, because it's the operational, the abstract machine can describe many different memory models, and we're trying to figure out what the best configuration is so that because we could make it very weak with this abstract machine, or we could make it much stronger. So we're trying to figure out the sweet spot for programmer efficiency and architectural efficiency before we release it to the public. And it looks like it's going to be a little bit more constraining than other weak memory models. So more constraining than Power and ARM, for example.
So you mentioned microarchitectural research. Do you have any class of workloads in mind for that?
So we're planning on running the spec benchmarks in Linux kernel just to stress virtual memory and the whole stack. We also wanted to, when we get our multi-core implementation up and running, we wanted to explore other multi-core benchmark suites, and we are definitely open to suggestions.
Do you have any spec score target in mind?
Specs for target, not at the moment.